Hi, welcome to week 10 of the Math 320 videos. In the final 2 weeks of this course, we will talk about derivatives. Now, you have all passed your calculus course, and so you already have some experience with differentiating functions. However, most of the time, you have been focused on differentiating functions by applying a bunch of rules to simple classes of functions. The functions you have treated can generally be summarized in the following list. 1. Polynomials and ratios of polynomials. 2. Exponential functions and logarithmic functions. 3. Trigonometric functions and their inverses. The rules that you apply are the power rule, the product or Leibniz rule, the quotient rule, the chain rule, and the derivative rules from the exponential, logarithmic, and trigonometric functions. In this class, we're not so much interested in the rote applications of rules. Rather, we wish to concentrate on understanding what it means for a function to be differentiable, and how we can start with the very basic definition of differentiability and arrive at various properties of differentiable functions and their derivatives. In the lectures this week, we will first introduce two definitions of differentiability. We'll introduce a limit definition as well as an epsilon delta definition. This is the same as what we did for continuity. There are situations where limit manipulations can be perfectly rigorous and give you the correct answers. There are also situations where you need to roll up your sleeves and actually use the epsilon delta definition. We will see a bit of both this week, and hence both definitions are presented. After doing some examples, we will finish up this week by showing how the basic rules of differentiation and differentiability follow from the definitions of differentiability, as well as from facts concerning limits that we have already discussed earlier this semester. If there is one takeaway message for this week, it's that all the differentiation rules you learn in calculus are not just rules that you must memorize. No, they are in fact necessary consequences of the definition of what a derivative is. If you just remember what a derivative is, you should be able to figure out the various differentiation rules on the fly, even if you don't memorize them. In this first lecture, we will define differentiation. This corresponds to material on pages 223 and 224 of your textbook. The definition of differentiability is exactly as you have become familiar with in your calculus class. A function f is said to be differentiable at a point c in its domain if the following limit converges. We first form the difference quotient for the function by taking f evaluated at a point x minus f evaluated at a point c divided by the distance x minus c. This difference quotient can be recognized as the slope of the secant line that connects the points c, f of c to x, f of x. We're taking the limit as x approaches c with the expectation that the secant line will become, in the limit, the tangent line to f at the point c. This tangent slope is called the derivative of f at the point c. Notice that this is a two-sided limit. We must consider the limit where x approaches c from below and also from above. Our definition of limit does not require evaluation of the argument at the point x equals c, which is good since the difference quotient itself doesn't make sense when x equals c, since we'll be dividing 0 by 0. Now, sometimes in order to prove that the limit that defines the derivative converges, we need to actually study the limit using our epsilon delta definition of convergence. To streamline stuff a bit, we can, at this stage, unwrap the previous definition and rewrite it using the epsilon delta formalism to make it easier to apply if we ever need it. Remembering that the statement that a limit converges uses the value of the limit as an ingredient, so the statement here for the derivative also uses the value of the derivative as an ingredient. A function f is said to have a derivative m at a point c in its domain if for every positive epsilon there is a positive delta such that if x in the domain has distance to c that is strictly between 0 and delta, then the quantity f of x minus f of c minus m times x minus c is, in absolute values, less than epsilon times x minus c. Let's digest this definition a bit. The second and third terms on the left-hand side with the minus signs flipped is the equation for a line that passes through f of c and has slope m. This is the point-slope form of the equation of that line, which reads f of c plus m times x minus c. So the difference is measuring the difference of the original function f of x with its linear approximation using its instantaneous value and slope at the point c. The inequality tells us that this approximation is better than any linear approximation, since the difference is less than epsilon times the linear quantity for arbitrarily small epsilon. So the definition is satisfied if the line through c, f of c with slope m is the best possible linear approximation of the function f near the point c. Let's just talk through how the two definitions are indeed equivalent. We start with the limit definition. The fact that the limit exists and converges to some number m is equivalent to using what we learned 2 weeks ago about limits of functions, that for every epsilon there exists delta such that if x is within distance delta of c, then the difference quotient is within distance epsilon of m. Notice that as usual, for computing the limit, we don't care about the value of the expression at c, so we only look for those x for which x minus c is between 0 and delta. Since x is not equal to c, we can multiply through by x minus c with impunity, and so the statement that the difference quotient is no more than epsilon from m is exactly the same as the comparison between a function and its linear approximation that we discussed on the previous slide. Every single step in this chain are given by implications, and so we see that the two definitions are equivalent. Having given you the two definitions for differentiability, a natural question for you to ask is, which one should I use? The two definitions being equivalent, either of them will get you to the correct answer. The limits definition is usually easier to apply. For many of the functions you may encounter, the difference quotient simplifies to something whose limit you can take pretty directly using just algebraic methods. So provided you know how to justify that the limit exists, or how to evaluate the limit, frequently, using what you have already learned in this course to date, you can more simply and more quickly justify the differentiability than trying to use the epsilon delta definition. In this lecture, we will give several examples using this method. There are, however, situations where the epsilon delta definition shine. In addition to the situation where the difference quotient do not simplify nicely, and hence the epsilon delta description need to be used anyway, we will see at the end of this week that sometimes when describing and proving properties held by derivatives, the epsilon delta definition becomes essential. So now, let's do some examples. The first several should be easy reviews for you if you remember how definitions were first introduced to you in Calculus 1. We start with the simplest case of the linear functions. Here, the function L has domain all of the real numbers and is given by the formula L of x equals mx plus b. From the geometric meaning of the derivative, we know that the derivative should equal to m everywhere. This is because, quite obviously, the best linear approximation to a line is the line itself. We can check that this indeed is the case using the limit definition. We can take the limit as x approaches c of the difference between L of x and L of c, all divided by x minus c. After expanding the terms, we see that the constant term drops out, and the two first-order terms can be grouped together. After the grouping, we can cancel out the factor of x minus c from both the denominator and numerator, leaving the limit of the constant quantity m, which of course evaluates to m. With this, we've shown that for any c in a domain, the function L is differentiable there with derivative m, exactly as we expected. Next, let us look at the quadratic function f of x equals x squared. Using the limit definition, we need to take the limit of the difference quotient f of x minus f of c, all divided by x minus c. Plugging in the formula for f, the quotient becomes x squared minus c squared over x minus c. The numerator can be factored into x minus c times x plus c. The duplicated factors between the numerator and denominator can be cancelled out, using that x minus c is non-zero in the process of taking the limit. Remember, when taking the limit, we discount the possibility that x is equal to c. So now we just need to take the limit as x approaches c of the quantity x plus c, which, being a continuous function, we can just substitute x into the formula to get 2c. Notice that in the final step we used a crucial fact, that we know the function x plus c, to which the difference quotient simplify, is a nice continuous function, and hence we can easily evaluate its value. When the difference quotient function becomes no longer so simple is when we need to use more care to figure out the derivative, using instead the epsilon delta argument. To summarize the result of our computation, this shows that at every real number c, the function f of x equal to x squared is differentiable. The derivative turns out to be 2c. This means that the derivative can be written as the function f prime of x equals 2x. In this next example, we look at the function defined only on the positive real line, with f of x being 1 over x. The algebra is a bit more involved, but the principle is the same. We first set up the difference quotient. Plugging in the expression of f being 1 over x, we find that the quotient to have numerator 1 over x minus 1 over c and denominator x minus c. The fractions in the numerator can be subtracted by taking common denominators. This leads to the numerator becoming c minus x over c times x. C minus x being the negative of x minus c, we can simplify the difference quotient down to the quantity minus 1 over cx. This is again a continuous function whose limit can be taken directly, and we find the limit to be 1 over c squared. This tells us that the function f is differentiable at every point c in its domain, with derivative minus 1 over c squared. Next, we will discuss several slightly more involved negative examples. In the previous three examples, the functions are of pretty simple forms, and they are proven to be differentiable at every point in their domains. The next three examples are different. First, we consider the absolute value function. By now, we probably all know that this function is not differentiable at the origin. Let's, for review's sake, see how this is proven. First, let us try to take the limit from above of the limit quotient. So we consider the limit as x approaches 0 from above of the quantity f of x minus f of 0 divided by x minus 0. Since we're approaching 0 from above, the value of x is positive. This means that f of x is no different from x. So we end up taking the limit of the quotient x over x, which equals 1. Next, we can take the limit from below. The initial setup is the same, but this time, since x is approaching from below, each x takes a negative value. So f of x, being absolute value of x, works out to be minus x. If we substitute this quantity into the limit, we see that the limit evaluates to minus 1. Since the limit from below and the limit from above disagree, the limit does not exist, and hence the function is not differentiable at 0. Next, let's consider the step function h with domain all the real numbers. H is defined to be equal 1 for non-negative x and 0 otherwise. When we take the difference quotient and take its limit from above, notice that for positive x, h of x minus h of 0 is always 0. So we're taking the limit of 0, which evaluates to 0. However, when we take the difference quotient and take its limit from below, the difference quotient evaluates to equal minus 1 over x, coming from the fact that for negative x, h of x is 0 and h of 0 is 1. The limit of minus 1 over x does not exist, and hence the function h is not differentiable at 0. Notice, however, that for every positive x, we have that the derivative of x is 0. And similarly, for every negative x, we also have that the derivative of h is 0. And hence, if we take the limit of the function h prime of x, either approaching 0 from above or from below, we will find that the limit is always equal to 0. And so we have an important lesson in this example, that the limit of the derivative exists does not mean the derivative itself exists. This function h is not differentiable at 0. However, it is differentiable at points that are not 0, and the limit of the derivative as we approach 0 converges. What we saw in the last slide about the step function should be contrasted with this function. Here, f of x is given by x squared times sine of 1 over x. And we set f of 0 to be 0. This value is separately defined since sine of 1 over 0 is not defined. When f is non-zero, using what you learned in your calculus courses, you know how to evaluate f prime. The derivative turns out to be equal to 2x sine 1 over x minus cosine 1 over x. And so, away from 0, the usual calculus computations show that the function has a derivative. Here, we are implicitly using many derivative computation rules that we haven't quite covered. Let's just take that on faith for this slide, as you have already seen them before in a calc class. However, if you try to take the limit of f prime of x as x approaches 0, you find that the limit does not exist. This is because f prime of x is the sum of two terms. The first term converges to 0 as x goes to 0. This is because sine of 1 over x is bounded, and so that the coefficient 2x going to 0 means that the entire term must go to 0. The second term, however, does not converge. As x approaches 0, cosine of 1 over x oscillates rapidly between minus 1 and 1 and never settles to a fixed number. I remarked that the convergence of the first and the non-convergence of the second term were both covered in week 8 of this course. So, with the limits of f prime not existing, we may wonder whether f is differentiable at 0. It turns out, however, the function is differentiable at 0. When we write out the difference quotient, since the function evaluates to 0 at 0, the difference quotient just becomes the function f of x divided by x, leaving us with x times sine of 1 over x. So as we discussed in the previous slide, the limit of this quantity as x approaches 0 is 0. So this function has a derivative at the origin, and it is equal to 0. So the takeaway from this example is in stark contrast to the previous one. In the previous example of the step function, we saw that the function's derivative may have a limit at a point, but the function may still fail to be differentiable there. In this example, we see that a function can be differentiable at the point, even if its derivative fails to have a limit there. Combining both, the key idea is that the derivative of a function in general need not be continuous. And this is something you should keep in mind going forward. Okay, this is it for this lecture. See you next time.